All right, so today we're going to cover a few different sections. We're going to start off by covering one section in Chapter 7, section 10, I believe. Let me flip back there. Yes. Okay. And this is called, well, specifically, this is called the Wilcoxon-Mannwhitney Test. Okay. This is just one test in an entire field called nonparametric statistics. Okay, this is just one test in the family of nonparametric tests. Okay, and so what do we mean by nonparametric tests? Okay, well, so far the only hypothesis test that we've really covered is the t-test, right? And in the t-test, okay, so this is just kind of, versus a t-test. So maybe wait, let me just write nonparametric tests versus parametric tests. And so far we have covered just one parametric test. We have covered the t-test, which is parametric. Okay, and what we mean by that is the t-test relies on the fact that there is the central limit theorem. Okay, and the central limit theorem says that when you repeatedly take random samples from any population, as long as those samples are large enough and you're looking at the sample mean will follow the normal distribution. Okay, and the t-test says, well, if you're going to estimate the standard deviation of that normal distribution, then you have to kind of relax the tails, and that's how we get the t-distribution. This sounds kind of familiar? Okay, so because it relies on an underlying distribution, namely the normal distribution, these are called parametric tests, because distributions are defined by parameters. So the normal distribution is defined by the mean and the standard deviation. And then there's other tests that rely on just known probability distributions. And anything that works that way, these are called parametric tests because they rely on known probability distributions. Okay, so I'll try to summarize that in just a couple sentences here. We've covered the t-test. The t-test relies on the central limit theorem, which states that sampling distributions of the sample mean that sampling distributions of the sample mean will have the form of a normal distribution. Okay. And so the tests that rely on known probability distributions are called parametric tests. And because we rely on this central limit theorem, the t-test has a few assumptions or conditions that must be checked, right? So because of this, because it relies on the CLT, we must check some conditions. Conditions or make assumptions. Okay. Do you guys remember what those conditions or assumptions are for using the central limit theorem? Okay, the sample has to be selected randomly. And then there's two others. The sample size must be large. Must be large enough, but not too large. Otherwise, we'll have problems. So basically, you just need to make sure your sample size is large enough. And we kind of left that definition of what is large enough a little bit vague. We just said, it just should be large enough. We said something around, sample sizes over 25 or 30, in most cases, are large enough. And so there's the question of, what do we do when the sample size is not large enough? Okay? Or, what do we do if you don't want to make assumptions? So, I guess large enough is sample sizes of 25 or 30 are usually large enough, or if you're going to assume that the population is normally distributed, then any sample is large enough, right? So if you don't have a large enough sample and you don't want to make the assumption that the population is normally distributed, what do we do? Okay? And so that's where we introduced non-parametric tests. Non-parametric tests don't rely on the central limit theorem or don't rely on the on a known probability distribution. Okay, so I'll just briefly write. So in particular, the condition is samples must be large enough or population must be normal, is assumed to be normal. Okay. So in cases where we can't make these, where this condition is not met, or we don't want to make this assumption, we turn to non-parametric tests. Okay. And so there's actually an entire, I guess, field within statistics called nonparametric statistics. And you can take an entire course on nonparametric statistics. But in this class, the Wilcoxon-Mann-Whitney test will be our only exposure to nonparametric statistics. And we're probably going to spend maybe half an hour on it, okay? So, but I guess our half hour is mostly to tell you that nonparametric statistics exists, when you would want to use them, namely when you can't apply a parametric test, and we'll cover how to actually do just the Wilcoxon-Mann-Whitney test. Okay, but yeah, like, you know, if you pursue additional statistics classes, you might see one offered called Nonparametric Statistics, and there's all sorts of literature on the subject. Okay, practically speaking, we will use the Wilcoxon-Mann-Whitney test when we have a small sample, and within that small sample we see an outlier, which gives us an indication that the population is not normal. Okay, so you know, practically, on a practical level, okay, we will use have small samples and there are outliers present you know, to indicate a non-normal population. Okay. In general, I guess I'll write this on the next slide. In general, non-parametric tests are less powerful than their parametric counterparts. Okay, so do you guys remember what power indicates? I talked about power, right? Yeah. Yeah. Okay. So what does it mean for something to have less power? Okay. Or what is power? You guys remember? Okay. Here. So I'll flip to the next slide here, if that's okay. Or was anybody still writing? Okay. Okay, so I'll just say, in general, non-parametric tests are less powerful than their parametric counterparts. Okay. So, so for example, like the Wilcoxon-Mann-Whitney test is the non-parametric counterpart to a t-test, and or t-test for two samples. So t-test for two samples, you look at two independent samples, and you say, you know, do we have evidence that the mean of one sample is different than the mean of the other sample? And the Wilcoxon-Mann-Whitney test is kind of the non-parametric counterpart to that, and it's less powerful. So just a quick review. Power is defined as 1 minus beta, or 1 minus the probability of committing a type 2 error. So what is type 2 error? So, okay, so 1 minus the probability of a false negative. So what would power then be? Yeah. So this is power is probability of correctly rejecting the null hypothesis. Okay? So less powerful means our test is not going to be rejecting the null hypothesis as often as it should. Okay? So a test that is less powerful will require more evidence for you to come to the same conclusion of rejecting the null hypothesis. Okay, and if we think about it, it kind of makes sense, because what we are doing is we are making fewer assumptions about the population, right? So in a parametric test, we make assumptions about the population, and based on those assumptions, we say we're making our conclusions, okay? With a non-parametric test, we're making fewer assumptions, and because we're making fewer assumptions, our data needs to be more convincing, okay? So, you know, if you're going to make a certain assumptions about, you know, where your data is coming from, then you know, small changes in the data could convince you of something, okay? But if you're not going to make any assumptions about where your data is coming from, then you know, you need to kind of see larger evidences of difference before you're willing to make that conclusion. Is that a reasonable thing to say? Okay. Well, it is. At least it applies here for non-parametric tests. Okay, so let's talk about the Wilcoxon-Mann-Whitney test specifically. And okay, so Wilcoxon-Mann, that's two N's. These were three people that worked on this test. Wilcoxon-Mann-Whitney test. In other textbooks, this might also be called the Wilcoxon rank sum test. Okay, the Wilcoxon rank sum test is conducted in a different way, okay? But the mathematical results are the same. Okay, they didn't know it at the time, but it turns out that the mathematical results behind the Wilcoxon rank sum test, Wilcoxon-Mann-Whitney test are pretty much the same. Okay, and because you use them in similar scenarios. So yeah, Wilcoxon, this guy did a bunch of non-parametric stuff. Okay, and so we use it to compare two populations based on two samples. Okay. But the funny thing is, or I guess the slightly odd part, is that when we write our hypotheses, we don't use the parameters mu, okay? Because that would indicate kind of a parametric test. So we don't say the mean of population 1 is the same as the mean of population 2. We have to kind of write out our hypotheses this way. So we would say, oh, sorry, let me just throw in there, based on 2 independent samples. Okay. Two separate populations based on 2 independent samples. Okay, so the null hypothesis is that the population distribution of Y1, or you can think of this as a group 1, is the same as the population distribution of Y2, or group 2. Okay, so that is our null hypothesis. We're just saying the 2 populations, the 2 respective populations of group 1 and group 2 are the same. So we're not saying anything about the mean of the population or anything about any parameters of the population, but just that the populations themselves are the same. And then the alternative, okay, we could have a non-directional. Non-directional will be one of the population distributions tends to produce larger values and the other population distribution. Okay, so even though I'm using the word larger here, because I'm not specifying which population distribution I'm talking about, this is still a non-directional alternative. If I have a directional alternative, it would be the population distribution. I'm going to just abbreviate this to popdist of, group 1 tends to produce larger values than that of Y2. Or, vice versa. Y2 tends to produce larger values than Y1, population distribution. Okay. So this one would be non-directional and this one would be directional. Is that okay? Okay, so we'll learn how to do this, I guess, by hand, which is fine, I guess. Again, most of our stuff is done via the computer. I think the important part in this non-parametric lesson is understanding these hypotheses, or how this test is set up, and the situations in which it applies. Okay. The test itself is a little bit quirky. Okay. So step 1 of the test is to take the data from both groups and sort them from least to greatest. Okay, so in our case, so our example, we're looking at data from the forest, and we are looking at soil respiration data. Okay, So I'm not exactly sure what soil respiration is. Has anyone heard of this? Apparently it's how much carbon dioxide the soil gives off in a certain amount of time or something, or I didn't realize that this is something we we record, but apparently it is. Okay, and we're looking at two parts in the forest. We're looking at, there's one area where there was lots of growth in the forest, and then there's another area where there is a gap in the growth. Okay, and so we're looking at data from two sections, and we're going to sort these from least to greatest. Okay, and so in the growth area, we have 17, this is moles of carbon dioxide, and then we have 20, 22, 64, 170, 190, and 315. Okay, and then over here we have 6, 13, 14, 15, 16, 18, 22, and 29. Okay? All right, and then so the next step is for each value, count how many values in the other column are smaller. Okay, and then ties are worth 1/2 each. Okay, so what we do is we look at this number 17, and we say how many values in the other column are smaller than 17, and we go, oh, 6 is smaller, 13 is smaller, 14, 15, 16, so I got 1, 2, 3, 4, 5. 5 values in the other column are smaller. For number 20, I look over here, 6 values are smaller. For 22, I got 6 values that are smaller and 1 tie worth 1/2 point. So this, we're going to write 6.5. If there was another 22 here, each one would be worth 1/2, and so we would have a 7 here. Okay? And then at 64, all 8 values in the other column, 1, 2, 3, 4, 5, 6, 7, 8, all 8 values are smaller, and so we can say, you know, 8 are smaller than 170, smaller than 190, and 315. Okay, and then we do the same thing for the other column, and we say how many values are smaller than 6 in the other column. Okay, and then so filling this out, I got 0, 0, 0, 0, 0, 1. At 22, I have 2 and a tie, 2.5, and then at 29, I have 3 values that are smaller. Okay, and then we sum these. Okay, so sum those, I guess, sum those counts. And then the larger sum is our test statistic U. Okay, I'm not sure why we've picked the letter U, but that is the letter that is designated for our test statistic. So over here we have 6.5 as our sum, and over here our sum, I believe, is 49.5. Okay, so our test statistic U is 49.5. Right. And then we're going to take this and look this value up in the Wilcoxon-Mann-Whitney table. Okay, so we look up, step 4 would be look up U in the Wilcoxon-Mann-Whitney table. Okay, and use of the table requires the designation of n and n prime. Okay, n and n prime are your sample sizes. Okay, the larger sample size is designated n. And the smaller sample size is n prime. Okay, so in our case, n is equal to 8. I'm sorry, yeah, 8, and n prime is 7. Okay. So we just go to the Wilcoxon-Mann-Whitney table with n equal to 8 and n prime equal to 7. So let me reference tables. Oops. Okay, so here's our Wilcoxon-Mann-Whitney table. So we're going to go to n prime equal to 8. I'm sorry, n equal to 8 and n prime equal to 7. So this is the, here I'll just copy this over. So this is the relevant row. From the Wilcoxon-Mann-Whitney table. Oops. Okay. All right, and so just like the T table, we say, okay, U is 49.5, so 49.5 fits in between 48 and 50. Okay. And so what we have here then is our corresponding p-values are written in italics. So the corresponding p-value is between 0.0093 and 0.021. Is that okay? And it's going to be closer to 0.0093 than it is to 0.021, but that doesn't really matter. So this is just a row in your Wilcoxon-Mann-Whitney table. So if you have your reference tables, you can kind of look through it and just make sure you can follow along. Okay. So are there any questions so far on just the mechanics of this test? Okay. If we were to do this in R, and we don't have to do it in R, we would do I think it's called a Wilcox test or something like that. You just punch in your numbers and go. And again, the hypothesis is not about any statistic mu or a parameter mu. It's just kind of in general, the distribution tends to produce larger values or smaller values than the other distribution. Okay. The values in the Wilcoxon-Mann-Whitney table are for a non-directional test. It says this at the top. Okay. The table provides selected values of the test in bold type, and the corresponding p-values for a non-directional alternative is in italics. Directional p-values are found by dividing the numbers in italics in half. Okay, so if we had a directional alternative, we would have to take these numbers and divide by 2. Okay? So let's just, I'm going to flip to the next slide and just say, you know, the conclusion that we make, so our p-value from the test is between 0.0093 and, I already forgot what it was, 0.021, okay? All right. So in this case, what would we do? We would reject the null hypothesis, and this means we have evidence that the population distribution of the two groups produce different values. Okay, our null hypothesis originally, if we're going to use these, our null hypothesis is non-directional, right? We didn't actually specify it, but it would have been something along the lines of the population distribution of soil respiration data for the growth areas is the same as the population distribution of soil respiration data for the gap areas. Okay, so we'd have had a non-directional hypothesis, or not. Our alternative is non-directional. The null is always has an equal sign, so the alternative is only the alternative. So our alternative is non-directional, but what does our data seem to indicate? Our data seems to indicate that the data from the growth section, the soil respiration numbers from the growth section, are much higher than the soil respiration numbers in the gap section. Right? And so, so even though our original alternative is non-directional, we can make a directional conclusion because we have found enough evidence to convince us to reject the null with a non-directional alternative, and our data supports a directional conclusion. So we can do that. Okay, so even though our HA is non-directional, you know, we have enough evidence to reject the null, and we can make a directional conclusion. Okay, so we can say we have evidence that the population distribution of soil respiration data for soil in growth areas of the forest tend to be larger, or tends to produce larger values. This is like such a chore to write. Tends to produce larger values than the population distribution of soil for gap areas of the forest. Okay. Is it that it? Yeah. So areas where there's lots of growth, all this to say that areas where there's growth in the forest give off more carbon dioxide than areas that don't. Okay, and we didn't have to make any assumptions about the parent populations. And in this case, I guess I should have pointed this out when we first started to look at the data. Let me make sure you guys have this finished writing before I flip the slides. When we look at the data, we see that we have small samples of 7 and samples of 8. Okay, so these are smaller than our sample size of 25 or 30 or more. So we have smaller sample sizes, and if we look at the numbers themselves, we see a few extremely large values, which would indicate kind of the presence of outliers and that our population is non-normal. Okay, so let me just flip back. When we look at the data, we see we have small samples. We have some, really large values like 315. These are much larger compared to, all of these values over here, and so. In this case, it is appropriate to apply the Wilcoxon-Mannwhitney test. If you were to use the t-test, the conclusions you make would not be valid, would not necessarily be valid. And that is because you are assuming when you conduct a t-test, you're assuming that the sampling distribution follows a normal distribution, which is not necessarily true when you have small sample sizes coming from a non-normal population. Okay, is that all right? There's more explanation in the text about, and nobody's asked me this where. In all my years teaching this, about where these reference tables are getting its numbers. Okay, so the reference tables, the numbers that exist in the reference table, they're based on kind of the probability permutations of the different rankings. Okay, so if you had, let's say you had 2 teams, okay, Team A and Team B, and if they were all equally likely to finish a race, in terms of their, if they're both coming from the, let's say, okay, let me back up. So let's say you have Team A and Team B, and we're looking at their race finish times, okay? We're looking at their race finish times, and they're both coming from the same distribution, okay? So Team A is just as equally likely to finish the race as Team B in the same amount of time, okay? But because of whatever random sampling, random variation, the times are going to be different, okay? And so we can rank, we can do this and rank all of the players in terms of who came first and who came last. And then once we get all of these values, we can then count, how many people were slower in Team B than this guy in Team A, how many people were slower than this guy on Team A than this guy on Team B, so on and so forth. And we can figure out every single possible permutation of these finish times or these values. And we can figure out, if we conducted this test and, counted up the sums, how often will we get, this test statistic of 49? or a test statistic of 50 or something like that when we count them up. Because usually if you have 7 on this side and 8 on this side, you're kind of expecting about, if you're looking at the fastest person over here, you're expecting maybe just 0 or 1 people being faster than the fastest person over here. And if you look at the second person, you're expecting only, maybe about 1 or 2 people on this side. You're kind of expecting about the same number for each of these things. And so, but they can get mixed up. So anyway, you don't have to worry about where these numbers are coming from. The reference tables that we have are trustworthy and reliable as far as these Wilcoxon-Mann-Whitney tests go. The Wilcoxon rank sum test is almost the same ideas and principles applied, except the test is just carried out slightly differently. So, but if you ever take another statistics class and they cover the Wilcoxon rank sum test conceptually in terms of how the scenarios in which it is applied are the same as the Wilcoxon-Mann-Whitney test. Okay, so that's all we're going to say for non-parametric statistics. The rest, and we're going to skip almost all of the other sections in Chapter 8. So Chapter 8 focuses entirely on paired data. Wilcoxon rank sum test, or not, Wilcoxon-Mann-Whitney test is for independent samples, right? So we've done t-test for independent samples. Another thing for independent samples is the Wilcoxon-Mann-Whitney test. And then we've also done t-test for paired data. And then the rest of Chapter 8 is a bunch of non-parametric tests for paired data. We could cover those, but I didn't feel it was necessary. So we're going to skip the rest of Chapter 8, and we're going to jump into Chapter 9. Okay, and so today's lecture is kind of, there's going to be a major thematic shift here as we do Chapters 9 and 10, which is now on categorical data. Okay, so why don't actually we take a short break here, and then we'll cover Chapters 9 and 10. So we'll say 10 minutes, and we'll do 9 and 10.